Cool. So thank you guys for coming. This is Mechatronics meeting 2 for the spring semester introduction part 2. The original plan was not to have a part 2 of this meeting, but since there were a lot of questions and stuff on Wednesday, I got answers to those things and am going to give them to you now. So this is an overview of the meeting. So we're going to do some airframe payload adapter discussion, which is probably the most important discussion here. Have some dimension updates and reminders. Wait, I wrote the payload. Well, whatever. We're only talking about it once. We're going to have a brief discussion about electronics, Wednesday meeting location, lab and safety trainings, PDR feedback, and then manufacturing and ordering. So we're going to start with the airframe payload adapter. So I'm going to preface this with, I think that, so we had mentioned this before, that there was going to be some adapter designed by Insure Leadership. Original plan was actually us, mostly me. That's actually transitioned to Shayla, who's leading the design on that. But regardless, you guys didn't have to worry about the design. But I think because we didn't mention it really much after that and didn't really give you guys much more information, that some of you guys might have forgotten about it a little bit or had it slip your mind or possibly just not totally accounted for it. And in complete fairness, we didn't really remind you guys about it or give you more information about it. And we certainly should have given you that information by now. So the information here is the information we should have given you before, now that it's all fleshed out. And also some options and flexibility to aid you in the fact that you're finding out this stuff a little bit later in the game than we were hoping to have gotten it to. So just so that we're totally clear on what this thing is, it's going to attach to one end of your payload, one of like the long ends, assuming your payload is roughly cylindrical shaped. It could be a box or something, but there's going to be some small end. And is going to attach to that. And this is going to aid it in sliding out of the rocket. By next week, or at the very latest the week after, but the target right now is next week, we should have a CAD mock-up of at least something that you can put into CAD and check out how it interfaces with the stuff that you guys are designing. The plan is to test it in Andy's CERT rocket. I don't know if you guys actually know that Andy is making a CERT rocket / has made a CERT rocket, but for those of you who know about rocket certifications, basically the high level is you have to build a rocket to certain specifications to get certifications to be able to buy certain powers of rocket motors. And Andy is doing this, so he has a personal rocket that is similar enough to the rockets that Inter-Airframe is building that we can do system tests. So we're planning on testing this payload adapter before we actually attach any of your payloads to it. We'll just attach like a dummy payload to it to ensure its functionality and then make any design tweaks as necessary before we actually put any of your payloads in harm's way. If any design changes need to come out of that, they will be purely functional, like changes made so that it functions better. So the goal is obviously to not make any changes, but if we have to, we are doing it so that nothing goes wrong on actual launch day for you guys. And we will let you guys know as soon as we get information from that test. The critical features that you guys need to be aware of is that it's going to take up the entire ID of the body tube, ID being inner diameter. The payload airframe adapter is going to be 6 inches in length, weigh 500 grams. There's going to be 2 sets of 3 quarter-20 hole patterns. So basically, you guys don't have to interface with 6 holes, just 3. So you're going to have 2 choices, basically. Tentatively, the plan is to have those be on a 3-inch diameter and an 1.5-inch diameter hole or circle, spaced evenly at 120 degrees. If you guys, is that clear what I mean by that? Okay, so yeah, just 3 holes on 2 different diameter circles. Those are technically pending some additional information. So we will see once Shayla gets some more design stuff done, what we're final. Sorry, people talking next to me. What the final diameters are. Okay. And the last thing is that we will have 3 evenly spaced at 120 degrees shock core pass-throughs. And I'm going to talk about what that means and the significance of that in a few slides, because I realized that we might not have been clear on what a shock cord pass-through is. So rocket body tube inner diameter. Last week I told you it is 3.776 inches. This is what happens when you don't read the spec sheet right. It's actually 3.9 inches. The reason that I thought that is because I thought that this is outer diameter, and it didn't. So I took 3.9, subtracted 0.062 twice, and gave you that number. I can confirm for you that it is in fact definitely 3.9 inches because I have now put the screenshot of the actual information from the site that we are buying it from. So that's not going to change. That is the number. I apologize for the week of incorrect information, but that's the number. Although I would like to remind you that just because the tube has an ID of 3.9 inches does not mean your payload can actually be 3.9 inches, because you're going to want some kind of clearance. You're potentially going to want some kind of shock cord pass-throughs. So it can be close to that. But if you make it exactly 3.9 inches, good luck actually getting it out of the rocket. You want to make sure that you let the airframe payload adapter do its job. Its job is to be that full distance and make sure that you slide evenly. So as long as you give it a little bit of clearance, you'll be all set. And just a reminder, this is nothing new, but the payload mass is 2 kilograms and the payload length is 8 inches. Okay. Payload rocket interface. So I want to go over a brief discussion of the anatomy of a rocket, because I realized that normally at this point we would have actually been in the lab and been able to show you guys a rocket, and we haven't been able to do that yet. So it might not be clear to all of you exactly how this actually works. So this model that you see here is actually Andy's CERT rocket. So this is a great example because it's very similar to something that the Indra Airframe groups will be working on. So this diagram on the left is not exactly what we'll be doing here with the Indra Airframe rockets. This is actually a diagram from competition rocketry last year, but it's similar enough. So the rocket starts completely together on the pad, goes up, and once it hits apogee, which is the point of highest altitude, it deploys something called the drogue parachute, and that's a smaller parachute to slow the descent somewhat, but not all the way to its final terminal velocity of ground hit, simply because if you deployed the biggest parachutes at apogee, then you would drift far, and you don't want to do that. You want to stay, relatively close to your launch pad. At that point, so you descend some on just the drogue chute, and then at some point later, when you detect that you're at some lower altitude, you deploy the main parachute, which is larger. And then under the combined drogue parachute and main parachute, you descend at a slower speed and you come to rest at the ground. At some point around the main parachute deployment is when you would deploy the payload. That's going to depend rocket to rocket. In this case, I believe that it's coming out just after the main parachute. So we get this stage. This stage is actually pretty similar to this diagram here, with one exception, in that in this diagram, the payload, which is this little brown rectangle, I don't know if you guys can see that well or not, is coming down under its own parachute here, and the nose cone has its own parachute. In this case, you're going to be tethered to the nose cone, which, if you're thinking, hey, I didn't know that before, you're right. You didn't know that before. But you shouldn't have to worry about it because it's going to be attached to a long piece of shock cord. So it's not it should land a decent distance away from you. It will technically be tethered to you, but it shouldn't affect you. It's not going to land on you unless there was some freak accident. So the way that the rocket itself will actually look is we have the motor section and fins down here. So this is where the actual propulsion comes from. This section right here is called the eBay, electronics bay. So this is where all the avionics, the altitude sensing, the parachute deployment, electronics, all that stuff lives. And then this is the nose cone. So it's the super, super high level explanation of what's going on. It's slightly different in Andy's rocket, but basically you'd have your drogue parachute here in this region where my mouse is, your main parachute here, and then your payload up here in this area here. So what you see on this image on the right is this top part here, but flipped upside down. So this is the eBay, which is this right here, and then this is the nose cone, and that's the nose cone right here. So this is actually the orientation it would be in when we're going to actually deploy the payload. So because the main parachute would be coming out of this part of the rocket, and that's going to be the highest point. So you're going to have the parachute, and then both halves of the rocket are going to be draped like under it, like in this image. That's just why it's upside down. So when we hit the set altitude, the black powder charges right here are going to be activated by the eBay electronics, and they're going to push the nose cone off of this section of the rocket. The nose cone is connected to the rocket here with shear pins, which are just nylon screws, basically meaning that they are intended to break with high enough loads, which the black powder provide by pressurizing this chamber. At this point, the parachute, the payload adapter, and the payload itself, which are tethered to the nose cone, are going to fall out of the rocket and descend. So that's roughly how that stack up works. But what I want to talk to you guys about is how the nose cone and the parachute are actually attached to this stack up. So we have a bunch of different options. So this wasn't necessarily initially part of the plan, but the mentors and I had a discussion about this and ultimately came to the conclusion that we want to give you guys these options. So I'm going to walk through them, and then your mentors and you guys can talk about which one makes sense for you guys, because basically the reason we're giving you so many options is so that it doesn't mess up any of the designs you guys already have. So any place that you see a like colored line that insinuates some kind of shock cord, something I want to note is that I just drew like closest, smallest line possible kind of thing, connections between stuff. They would actually be more slack to allow things to be further apart when they hit the ground in these connections. Like this red one right here, like if the payload and the nose cone were tethered right here, it wouldn't actually be this short of a piece of shock cord. It would actually be way longer than that, but I just didn't want to draw a coil. That wouldn't help.
But all cords will stay within the rocket. There will be no external cords.
Yeah. No, it would. Yeah. Thank you for mentioning that. That's just my drawing skills and lack thereof. So your first option would be to connect the parachute to the payload adapter and the nose cone to the payload. Your second option is to attach both the nose cone and the parachute to the payload adapter. Third option would be to attach the nose cone and the parachute to the payload itself, thing you guys are making. Fourth option would be parachute to payload, nose cone to adapter, and then like fifth option, which is really more than the fifth thought. There's like a bunch of things that you could kind of create out from this, but I'm just kind of lumping it into one category, would be attaching the nose cone and or the parachute to like the side of the payload or something like that. So basically what you guys need to take away from this is if you want to connect both things to the payload adapter, you have the ability to do that. So that means that the payload adapter, which we're designing, will have the ability to connect to both of these things. So if you don't want to worry about them connecting to your payload at all, and just want to worry about connecting to the payload adapter and everything else is handled by the payload adapter, that's fine. You can do that. The thing you need to remember, though, is based on where the parachute is connected, that's going to affect what is up and what is down. So like in this left case here, this is going to descend with the payload adapter on top of the payload. So when you hit the ground, the payload's going to hit the ground first. Whereas if you went the other way, say this middle one where you attach both of them to the payload, then as soon as this falls out of the rocket, the adapter is going to flip around and be underneath the payload itself. So the payload adapter is going to hit first because obviously the payload is being held onto most directly by the parachute. And then this like purple example over here on the far right, would be that like third case, I guess, where if you hold on to the payload from the side, it's much more likely that the payload is going to land sideways like this, which for some of your designs is something you want. So this is just a game of how many connections on your system do you want to have to deal with? Like which things do you want to actually interface with? And what do you want to hit the ground first, the adapter or the payload or the side of both? Yeah, and so you guys will have that conversation with your mentors about what makes the most sense, and we can help you guys to make that happen. The one last thing I want to note about that, though, is pass-throughs. So as you see on some of these where the lines like kind of went outside the rocket, of course, the shock cord can't actually go outside the rocket because that's not how rockets work. Everything needs to stay inside. So basically, if you're going, like, let's take this pink example here. If you're putting a line up and past the payload from the nose cone up to the payload adapter, then you're going to need some kind of like slot or something or some region where that shock cord can physically pass by. So you have to leave a little bit more clearance in a region. It doesn't have to be the entire, like a circle shrunk down. It could just be like a notch or something like that, but you'd need to leave space. And that's referred to as a shock cord pass through. It's a region where the shock cord can pass by something. How thick is the shock cord? Good question. There's different types of shock cord. I need to check with Airframe on which one they're planning on using. Depends on which one they bought. I don't know. But I will get that answer for you. Good question. Yeah. So, and just so you guys are aware in terms of pass-throughs on the payload adapter, because again, obviously we're designing that. So that is going to have pass-throughs. It's going to have 3. So the plan is to have 3 at 120 degree spacing, probably clocked 60 degrees from the interface holes, if that makes sense. So if your interface holes are here, here, and here, then you'd have your slots here, here, and here. But the final verdict on that will ultimately be what Shayla does. But again, we should know that over the next week. We should have a CAD model for you guys to work with. So, all right. Before I move on, does that make sense? I know I just dumped a bunch of information on you guys. Does this answer questions you guys had about this interface and the way it works and why we have it and what variables we have to tweak and all that stuff? All right, cool. And if you guys have any questions, of course, you can ask me or your mentors after as well. Okay, into some easier stuff. Electronics that we're using. We did already talk about this. We did tell you guys, well, mostly before what we're using. The only difference is the battery. And we actually chose this battery because it's smaller. So this should help you. So the main boards are Arduino Nano. I have some specs listed for each thing. It's only 7 grams, 18 by 45 millimeters. Those are the XY dimensions. Spectre. Battery is this 2-cell LiPo, 33,000 milliamp hours. That's an image of it here. And then we're using the L298N boards for motor controllers, which you can see here. And we put CAD models for all 3 of them in GrabCAD for you guys to use. So if you want to take any dimensions of anything, place it inside of some preliminary CAD you guys have, anything like that, those models are there for you guys. And these links are also go to the product pages for them. So you guys have access to this PowerPoint and you can go check that out. Okay, Wednesday meeting location. So as you guys know, Wednesday will be our first meeting in person. Some of you will be in the lab, some of you will be in the tent. Let your mentor know if you have a preference for this week. I haven't fully finished allocations for that yet. It might not end up mattering for a lot of you guys too much this week because I don't know how many of you guys are actually at the phase of doing some actual builds. It'd be great if you are, but if you're not, I totally get it. I don't think most of you are. But if you do have a preference, be sure to your mentor know, and I will be announcing locations for each team either tonight or tomorrow morning in Intermech General. Okay, trainings. So Northeastern uses the BioRAF portal to manage university-wide lab safety trainings. Link to it's here. In order to work in the actual ARNU lab, there's a set of those trainings that we have to complete. This isn't just you guys, this is us too. We all have to do it. The 4 of them that I listed here are the ones that you have to do. The lab safety refresher, because I believe you're all new to the club, I don't think any of you guys need to do. So it should just be the 1st, 2nd, and 4th. If you've already done the fundamentals of laboratory safety, but it's expired for whatever reason, then you'd need to do this one. So it's a total of 3. When you've completed those trainings, there's a form here. This is internal to the club, just so that for our records, so that we know that you've completed the training, so that you're allowed to work in the lab. In addition to that, there's also a internal club safety presentation that's run and managed by the CSO, Chief Safety Officer, which this semester happens to be Emma. So we have easy access. It contains some safety info that's more specific and relevant to ARNU members than some of the BioRAF trainings, because the BioRAF trainings are more generic for like lab safety in general at Northeastern, whereas this was put together by us about the specific stuff that we work on. So you may end up finding that this ends up being more helpful. So that's the hope, is that it kind of pares it down to do a lot of the information that you guys really need to know. But you also do need to do the BioRAF trainings, because that's not an us requirement. That's Northeastern saying that. That is scheduled for, so we're scheduled to receive this presentation next Monday from 8 to 8:30. Emma's going to give that. I believe if anything changed with that, I'll let you guys know. If you guys can't attend next Monday, let Emma and I know, so that we can provide you with an alternate time to attend it, just so that you can get that all set. All right. I'm not going to actually go through this. This is for you guys to go through, but I'm actually done with the PDR feedback. So these are all hyperlinks to the docs for you guys to look at your own PDR feedback. It's also in the drive. And if you guys want to actually watch the PDR videos as well, I've trimmed that recording down to the PDRs for each team. So in the recordings folder, you guys can find the videos of both your presentation and the like discussion Q&A section after together as a video. So I would encourage you guys to read these docs and potentially skim over those if you don't remember exactly what happened or anything like that. All right, and then I think the last thing, is manufacturing and ordering. So our budget has officially been approved. Professor Goldstone has generously offered once again for this semester to fund the project, so we can spend money. So if you need anything 3D printed or laser cut or anything ordered for prototyping or anything like that, let myself and your mentor know, and we can potentially get that going. Starting either next week or the week after, we'll be discussing these different manufacturing methods, 3D printing and laser cutting, in a group setting. But in the meantime, if you guys have any specific questions or things that you think you want made for this, through these methods for prototyping, just let your mentor know and they can help you guys out before that. So yeah, that is that. Do you guys have any questions about anything that I went through, anything that I didn't go through, that you do have questions about, or are we good?